been talking about subatomic particles and isotopes and how isotopes differ in their mass because they have different number of neutrons. Now we're going to focus on outside the nucleus and the electrons and where do electrons really exist. There was a previous example here that talked about electrons moving into a hotel, but it was kind of goofy, so we skipped it. So we want to kind of ignore this part and just look at where do we really find electrons? Well, they're in electron clouds. So what does that mean? That means that they can be in a huge area all over the place. They aren't concentrated just in one area. Okay, so they're in this area outside of the nucleus. And a lot of times when you're in junior high, they have you draw these Bohr models that these are where your electrons are. We are not learning that way anymore. Okay, we have a nucleus in the middle. And then we have electrons that can travel wherever they want, all over outside the nucleus, just like this. They don't have a path. They go wherever the heck they want to go in this cloud. So we call this huge area out here the cloud of electrons. Okay, and that's how we want to look at the atomic model. So we have that electron cloud. And then we have certain energy levels. We have certain areas within this cloud. This would be one. It's further away than this area, which is further away than this area. So there's certain areas that are called principal energy levels. And then within those, there's different levels that we find called subshells. Okay, so for example, we would have the nucleus, and then we might have this principal energy level here that looks like a sphere, and an electron can fit anywhere around in this area. And then we'll have another shell. Again, electrons can go anywhere in this area. Okay, so they're not just going to travel in that circle, but they're going to be within that area. Then we might have a shell that looks more like a dumbbell, and the electrons are going to be all within this area, traveling all around. And then we might have another ring that's a little further out, and electrons can be all over the place in here. Okay, and I know that looks like a mess, but that's what electrons do. They travel all over the place. So we have this whole huge electron cloud. Then we have these areas that are further and further away from the nucleus in different shapes, and those are our subshells. And then we have these orbitals, which is the area where the electron actually travels. Okay, so the subshell is a set of orbitals, so there might be more than one orbital in a subshell. And then the orbitals where those electrons are traveling in that crazy pattern all over the place. Each orbital can hold up to 2 electrons. So if we have this circular orbital, which is an s orbital, there can be 2 electrons inside of that. We could have a p orbital, and we could have 2 electrons here and 2 electrons here. Okay, so that's an example of how we find our electrons. So how in the world do we relate this to the periodic table? Well, we have 4 different subshells that we can have within an atom. The S is circular or spherical. The P is dumbbell. And then D and F get really complicated, so we typically do not draw those. S begins in energy level 1. Now, if you look at our periodic table, we have 1, 2, 3, 4, 5, 6, 7 rows on the periodic table. These correspond to our energy levels. So a row on the periodic table is an energy level. So if you look here, we have energy level 1 right here. It contains hydrogen and helium. And typically what I tell my students to do is rewrite helium over here because it acts more like everything in this column, even though it is a noble gas. Okay, so we have this area right here, and these 2 columns right here are the S subshell. Okay, so we have this S subshell, and we have first row, and you can see there's an S subshell for row 2, row 3, 4, 5, 6, 7. These 2 rows are the S subshell. Okay, this has 1 orbital. Okay, and it can hold 2 electrons. So the S is going to be a circular subshell, and 2 electrons can be found in that. This column represents 1 electron in an orbital. This column represents the 2nd electron in that orbital. So any of these s orbitals can hold 2 electrons. Column 1 represents the first one, column 2 represents the second one. So that's how that relates to this chart. The p sublevel begins in the 2nd energy level. So this is our 2nd row. You can see here we've got an s sublevel, and then you're going to read the periodic table just like a book. As we go across here, we go from number 4 atomic number to number 5 over here, okay, with boron, and this is our P sublevel. There's 3 different orbitals. Again, each orbital holds 2 electrons, so that means we can have a possibility of 6 electrons. 1 is represented by this column, 2 is represented by this column, 3 is represented, 4 is represented here, 5 here, and 6 here. And again, those lines could go all the way to the bottom here. I just didn't draw them. Okay? So you can see that each column represents 1 electron that can fit into the P suborbital or subshell. Then we have this D area. It starts in the 3rd energy level. Okay, so we've got this 3rd row is our 3rd energy level, and this right here is 3D. Even though it's in the 4th row, it's called the 3D energy level, and we'll get into that a little bit more. This is our 4D, this is our 5D, and this is our 6D. Okay, so you can see that the D's do not match up with what row they're in. They're 1 row below their energy level, and I'll explain that a little bit more later. So we've got a 3S, a 3D, and then we go over here, and this is a 3P area. Okay. When we get into the D, you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. These, again, each represent 1 electron. So the D orbitals, or subshell, can hold up to 10 different electrons. Each 2 columns represents an orbital. So this would be 1 orbital. This would be a 2nd orbital, this would be a 3rd orbital, a 4th, and a 5th. Okay. Each orbital holds 2, so that gives us a total of 10. And then our F is going to be down here, and we'll get to that a little bit later. So we're going to start writing electron configurations. We're going to start showing where the electrons are located within an atom. A lot of times we use box and arrows. So if we wanted to do hydrogen, hydrogen only has 1 electron. So we would draw a box, and we would represent it with 1 up arrow. Okay, pretty easy. So when we get further than hydrogen, though, when we get down here where we have a lot more elements, we have to represent each of our subshells. The P subshell can hold 6 electrons. Each orbital can hold 2. So we draw 3 boxes, because when we have a full P orbital, we're going to have a total of 6 different electrons. Okay. If it's full D, we can hold up to 10. So if we have a full D orbital, we would have 10 electrons. And then F holds 14, so we have to draw 7 boxes. So anytime we represent an S, it's 1 box, 1 orbital. P, 3 boxes for 3 orbitals. D, 5 boxes for 5 orbitals. F, 7 boxes for 7 orbitals. Okay. Again, if you look here, it corresponds exactly to our periodic table. S section in the periodic table, 2 boxes. P section, 1, 2, 3, 4, 5, 6. Okay. D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those boxes are represented here. Remember that 2 electrons fit in each box. So 2 columns on our periodic table represent 1 box or 1 orbital. Okay, so let's try to do a few of these. Let's start with lithium. If we have lithium, we're in our 2nd row. So what we have to do is always start at the lowest energy level, which is always going to be the 1st row of the periodic table. Okay, right here, electrons fill sublevels so that the total energy of the atom is minimized. So we're always going to start with the least amount of energy, which is always the top row of the periodic table, right here. So we always start in row 1. So we would write 1. We're in the S section. Okay, so we're going to write S. And then we would have to fill up both boxes. Remember, I told you to move helium over here, and forget that it's over here. So we would fill both of these boxes before we can move down to the 2nd energy level. That is always true. Another rule, if we look here. Place electrons in unoccupied orbitals at the same energy level before doubling up, and two electrons that occupy the same orbital must have different spins. These are our three different rules we always have to remember. Electrons fill so that the total energy is minimum, means that we're going to start at the bottom, and then we're going to write in our electrons one at a time. Okay? So we've got our box here. Each box represents an orbital, and we said that two electrons can fit into our S box. One goes up and one goes down. Okay. So we have to show that's full in the first energy level before we can move down here to our second energy level. Lithium falls right here. Okay, we're in the second energy level and we're in the S section. So we would write 2, and then we would write S. And since we're in the first column, this time we're not filling our orbital, we're only placing one electron in it because we're in that first column. So it would be 2s1 with one arrow pointing up. Okay, that's where we're going to stop for today, and let's do a little practice.